Right, so you can see the structure here. It's got, instead of one multiplier, it's got two multipliers. So we have to account for that, and that's related to the two different constraints that we have. We have a G constraint and an H constraint. So the example, the plane given and the paraboloid also given intersect in an ellipse. Find the point on that ellipse closest to the origin. All right, so that's telling us that we're going to need a distance formula. All right, so what I'm going to do is go back to something we talked about last class, I think, and that is to say that we're going to establish our distance formula to be a function of the three variables, but specifically not d equals, but d squared equals. So I'm going to say f of x, y, z is equal to d squared, which is equal to, now this is the good news, closest to the origin. The origin has coordinates 0, 0, 0. So x minus 0 squared, x squared, plus y minus 0 squared, y squared, plus z minus 0 squared, z squared. All right. So from this, I can establish my partials. Two x, 2y, plus, and 2z. So that's not bad. I have my two constraints, all right? So we need a point on that ellipse. The plane and the paraboloid intersect to form that ellipse. So basically, I need a point that's on the plane and also on the paraboloid that is closest to the origin, all right? So any point along this ellipse here, but it is the conjunction between those two, all right? So I have my two constraints, one of which I'll call G, and that's going to be x plus y plus z minus 12. And the other is going to be the paraboloid. Same idea. We want to set it equal to 0, and then set it, replace the 0 with a new function name. In this case, we already use g, so we'll call it h. X squared plus y squared minus z. All right. So h is going to be x squared plus y squared minus z. And I need all those partials. So dg partial g with respect to x, one across the board, so that's nice. So 2x, 2y, and negative 1. So the partials aren't bad. And the structure is the same, right? It's just we need to create different forms of the equation because it's accounting for either this multiplier or that one, so the addition. So the lambda multiplied by the g partial, and the mu is going to be multiplied by the h partial, right? So that's going to give us our first Lagrange equation. Then after that, we'll get our constraint equation, but that's for a different moment, I suppose. Okay, so we'll get to that in a sec. So I'm looking at 2x equals 1 times lambda plus 2x times mu. And we'll have 2y is equal to 1 times lambda plus 2y times mu. And then 2z is equal to 1 times lambda plus negative 1, so minus 1 times mu. It'll all clean up in a minute, but I'll get my constraint equations, which would be 0 equals x plus y plus z minus 12, and 0 equals x squared plus y squared minus z. All right, so that actually gets us back to the original equations for the constraints, right? Because they were just the boundaries to begin with. They weren't even asking for the inner areas, which is slightly different, but doesn't really change anything. All right, so now I have to do algebra. Fun algebra. So it's just a matter of identifying what the most convenient thing to determine would be. Right? So we have a bunch of different relationships here, and it's all kind of a mess. Right? So this one seems to be probably the cleanest out of all of them. Right? If I were to take the sum of this equation and either of these two, then maybe I can do something about the mu's. Right? So that's something to keep in mind. Right? You could also try to eliminate a variable here. Right? If you do that and then maybe so work the first two together and then combine that with the third one, then maybe you can figure out which one is the best way to cancel it. That would be my recommendation. So try to cancel a variable here and then use that result against one of these and try to cancel a variable and then see where that gets you. All right? So why am I saying all this and not doing it? Because I'm 2x minus 2x mu. All right, but you have a GCF there of 2x that can be factored out. Whether or not that's a useful next step is debatable, but it's something that we can do, so we might as well. All right, I can do the same thing with the second equation, and I'll just kind of cut to the chase there because it's got the same general structure. So lambda would be equal to, because I'm just going to subtract the 2y lambda from both sides and factor out a 2y, times 1 minus mu. All right. So from this relationship, I can actually draw a nice conclusion, right? Because I set these two equal to one another. I get 2x times 1 minus mu is equal to 2y times 1 minus mu. I don't know what mu is yet, but I do know that a consequence of this has to be that x and y are the same, because they're the only things that differ from one side of the equation to the other. So that's going to allow a substitution down the line. All right. I can also solve the third equation for lambda. And when I do that, I'll get 2z plus mu. All right, the idea being that hopefully we can be able to flesh out one or more of the variables at some point. All right, but just going off the idea that x is equal to y, we can take that and look at our constraint equations, do a substitution there, and see where that gets us. All right, so if I oops, I need to do that. If I substituted either an x for a y or a y for an x, it really doesn't matter. Replace one variable with the other. I get 0 equals, I'll replace the y's with x's. So x plus x, so 2x plus z minus 12. And for the other one, it would be x squared plus x squared, so 2x squared minus z. All right, so I have two equations now with two variables. So I can further the cause here and ultimately, hopefully, solve for one variable in terms of the other, all right, in terms of a numerical value. All right, so I'll solve for z. z is equal to 2x squared, which brings these two guys together through substitution to give me 0 equals 2x plus 2x squared minus 12. All right, so we're kind of on the road here. Clean it up. Chop everything in half, reorganize. So we'll be looking at x squared plus x minus 6 equals 0. All right, factor if factorable. Or you might consider completing the square or something like that. In this case, I think we're good, right? So x plus 3, x minus 2. So we get solutions x equals -3 or x equals 2. Now we know the relationship is that x and y are the same, so that means that if x is equal to -3, then so is y. If x is equal to 2, then so is y. And we also know how to get z, because we have a bunch of different relationships, but the most useful one here is that z is equal to 2x squared. Right, so I'm going to take my x value, square it, so 9 times 2 is 18. Right. So z would be equal to 18. And then I'll take my 2, square it, 4, and multiply that by 2, and we'll get an 8. All right, so we have two possible ordered pairs here, -3, -3, and 18. Also 2, 2, 8. All right, so the question becomes, all right, now what? Like, what are we looking for here? And, you know, we started this problem last class. I'll come back to that in a sec. I just need to look here. Find the point on the ellipse closest to the origin. All right, so out of these two possibilities, one of them has to be closer to the origin than the other.
Wouldn't it be minus x minus 10 and x plus 2? Oh, you have that positive. I ended up with everything times negative.
Oh, okay. All right. All right, so we're looking for the point that's closest to the origin. Now, you might say, well, this one just feels like it's closer to the origin than this one, but, you know, we do want to verify this. Right? So the way we would do that is to go back to our distance formula. All right? Because if the squared distance is smaller, then that one would be closer. All right, what we get out of this idea of Lagrange multipliers is the concept of extrema. All right, so it doesn't categorize it as maximum or minimum. All right, it'll give you extreme values. It's just a question of whether it's a max or a min. So one of these is a max, one of these is a min. Maybe they're both max, maybe they're both mins, but if there are going to be extreme values, it must be one of these 2 points. All right, so the bottom line here is that you can't just leave it here and say, well, it's at these 2 locations. So what we'll do is we'll apply the distance formula. And you could look at squared distances, or you can just use the actual distance formula. We'll do it for each point. So -3, -3, 18. The distance, it's going to be large. So 9 plus 9 plus 18 squared. So maybe I don't want to do that in my head. Well, 81 times 4 is 364?
It's 18.5 is the distance.
18.5?
Is the distance.
Okay. But now I need to know if that's 364. Because
Don't you just know that the 2 8s the minimum because the squared component of each of them is smaller than the other one?
yeah, but you still have to demonstrate it. Otherwise, you shan't be receiving full credit. 324. I said 364. We're dumb. So 324. And then at 228. Four plus 64. Say it again.
8.5.
8.5. Well then. Okay, so point closest to the origin would be the 0.228. Of course, satisfying the constraints, because the point closest to the origin would be the origin, if the constraints weren't there. Old derivatives and things like that. There's a nice little consequence that comes from it. I mean, there's a rule that expands into 3-space, but I wanted to actually take it back to 2-space for a second and just work with a function in terms of x and y set equal to 0. So I'll do it, you know what, I'm just going to throw in an example here and I'll take it as a typo if somebody wants it. Let's say you have x squared plus y squared equals 16. I'm just trying to remember what I have in my Calc 1 notes / high school calculus / AP calculus / every, it's all the same. Find dy dx. I think that's the problem. If you're to find the derivative of this, you'd have to use implicit differentiation. All right, so what you would do is take the derivative of the x term the way you normally would, so 2x. But really, there's an implied dx there. The implied part of implicit. Plus, which cancels out immediately, so you never needed to write it, but I'm doing it for a reason. So then 2y times dy dx. The idea being that x could itself be another function that requires a derivative to be taken. If that's the case, then a good habit to build is to say, well, I'm going to take the derivative of x with respect to what? Well, x, so it doesn't matter, I can cancel it out. But if it was with respect to s or t or any other variable that we've worked with throughout the semester, then theta, then it would have a multiplier. In this case, it cancels out, right? So does the 2's. So lots of things cancel out. You end up with x plus y dy dx equals 0. All right. And so when I solve for dy dx, I'm subtracting the x and dividing by y. All right. Now, this is something that I've always done with my Calc 1 classes. It's the first example I do with implicit differentiation. I explain this problem, and then after that, it's off to the races. Now let's use this skill, and with the promise that sometime later on in Calc 3, you'll get an explanation as to, the benefits or why this tends to work the way it does. This is kind of that moment, and it has to do with partial derivatives. So we have this generalized form of it, which I'll take you through in a second. But the one thing I want you to take note of here is the negative reciprocal relationship between the variables on the left-hand side and the variables on the right-hand side. And then look at our definition below. As we go into 3-space, we have a negative reciprocal relationship between the variables on the left and the variables on the right. Right? And that's consistently the case. So you can come up with your partial derivatives with respect to any variable in implicit form just by knowing what the individual partials are for your main expression. So more on that in a few minutes. But let's focus on the general form. So this is a little mini proof. Whatever that means. Number 10 on the test. So if I'm looking for the derivative of this, well, it's a function of two variables. So I could be looking at the partial derivative with respect to x, but then x itself could be its own function. All right, so, oh, I'm assuming that it's dy dx, by the way. That's what we're going for. Probably should say that in there. Or I might take the partial derivative with respect to y, in which case I'd have a dy dx to multiply by. Right-hand side's equal to 0. So there's really...
Partial derivative or?
No, it'd be an ordinary derivative because it is a function y with respect to x.
No, I mean for the active functions.
For
Those
these?
partial derivatives, yeah.
Yeah, these would be partial because it's a function of two variables. When it's a function of one variable, it's not partial anymore. All right, so this cleans up because this cancels immediately. And if I want to solve for dy dx, I'm going to subtract the partial with respect to x and divide by the partial with respect to y. If you want cleaner notation, you might say negative f sub x over f sub y. All right, but basically we just proved that the negative reciprocal relationship holds in 2 space. It's a little bit more complicated in 3 space. It's not terrible, it's doable, but it's not something I would ask you to do on a test, so I don't go over it here. But basically what you would do is you'd have partial with respect to x times dx dx plus partial with respect to y times dy dx plus partial with respect to z times dz dx equals 0, and then you solve for the relevant pieces. All right, so it's not bad. It's just it doesn't advance the plot. That's really what I'm getting at. Welcome to my world. So when we're dealing with a function, even a nasty function like this, just finding the derivative. Now this is a Calc 1 problem, right? If you look at it, this is implicit differentiation in Calc 1. Product rule, nasty product rule, not too nasty, not fun, but not too crazy. But after you do all that work, you get your dy dx's out of that. You'd have to solve for, like, you'd have to do the algebra to get dy dx alone. This new method allows us to find the partials. So use this technique, find the partials, and just divide them in the appropriate ratio. All right. So it's one of those things where my first reaction when I saw this is like, wow, that would have been nice to know back in Calc 1. But then you immediately follow that thought with, well, then I would have had to know partial derivatives back in Calc 1, which requires me to know all about derivatives to begin with, which means I would have had to know all of Calc 1. So it's a stupid thought, but it was a thought nonetheless. So I'm going to find partial with respect to x. All right, so much easier to do because now it's not product rule anymore. Or okay, maybe in some cases it could be, but typically not as crazy as it would be. So the derivative of x would be 1, so we're looking at y squared. Now for the second piece, we do have two factors, each of which contain an x. So we're stuck with product rule there. So first times the derivative of the second, so times negative sine x, plus the second cosine x, times the derivative of the first, which would be e to the xy multiplied by the derivative of the exponent, which would just be y with respect to x. All right. I can't remember if it's exactly the same as the problem that we did like a week ago or 2 weeks ago, or if it's just similar enough, but it's like the second day we did partials, I think. So anyway, we could clean it up a little bit. Y squared plus sine x e to the xy minus little y cosine x e to the xy. It really doesn't matter. We didn't even have to clean it up to begin with, because next step is on to the first order partial with respect to y, in which case we're getting 2xy minus, now this one only has one term that contains a y, so that's good news. So we treat the negative cosine x as a constant multiple, voice cracked, times e to the xy multiplied by x. All right, so what I'm looking for, and this is the beautiful byproduct of this concept, the derivative of y with respect to x. All right, so again, our partials only come from the left-hand side of the equation, the part that's set equal to 0. They call that w. I think that's actually a w. I don't think it's, what was it? Omega, lowercase omega. But yeah, the beautiful part about this is if you know that it's a negative reciprocal relationship, there's no real rules to remember. Right? I'm just going to take the negative partial of x, so negative all that stuff, and divide it by the partial of y. So negative reciprocal. So negate this. That goes on top. Keep that the way it is. Put that on the bottom.
Why do you switch to the top and bottom again? Or is it, oh, no, the proof there.
Yeah. All right, and so that leads us to number 5, which doesn't look exactly the same, but it follows the same format. So if I'm looking at partial z with respect to x, then what I need is partial x divided by partial z. Partial z with respect to y, I need partial y with respect to partial z. All right, so that's telling me that I need to get everything over to the same side. Get my partials. With respect to x, it's just what, negative yz? With y, it's negative xz. And again, that relationship, it's the negative reciprocal. So your question is giving you the recipe to find your answer. So then I just need my partial with respect to z. Oh, sorry, I'm calling it partial z. It's not partial z. It's in terms of z. Because this is a new function.
So why didn't it still say partial z with respect to x?
That's ultimately what we're looking for. You'll see in a second. Because this is partial w with respect to, what did I do first, x? Partial w with respect to y. And the last thing is partial w with respect to z. All right, so that's e to the z minus xy. All right, so again, this is the same as saying, we can call it f sub x is negative yz, f sub y is equal to negative xz, and f sub z is equal to e to the z minus xy. All right, so when I'm looking for the partial z with respect to x, I need negative partial x over partial z. So negative yz over e to the z minus xy. All right, and that's what you would get if you took the derivative of this implicitly. So if you had, you would take the derivative of this e to the z times the derivative of z with respect to x, so dz dx, minus each of these treated as a variable, so product rule. So first times the derivative, first and second times the derivative of third, first and third times the derivative of second, and so on, all with dx dx, dy dx, dz dx, all of that mixed in there, solving for dz dx, ultimately in the end, you would get this as a result. All right, do that all again and solve for dz dy, you would get what we're going to come up with in the next one.
Since it's a negative f of x, wouldn't the two negatives cancel out and make that positive?
Yeah. All right, so partial z with respect to y is the last part of it. So negative partial y with respect to z over partial z. So negative xz, clean it up if you want, over e to the z minus xy. And a nice star for you on number 6. This one's not too crazy, just asking us for the partial z with respect to y, which means that I need to determine my partial, because we're defining this function as w, so partial w with respect to y. All right, so not too crazy. All right, we're going to get a 2y times x, or 2xy. The z cubed is going to go away, but then we got to deal with the trig function, but it's still not disastrous. All right, so derivative of sine is cosine, so plus cosine xyz multiplied by the derivative on the inside with respect to y, which would be just xz. All right, so then, I mean, you can clean that up a little bit if you want, but I don't feel the need. Partial with respect to z, 3z squared plus cosine xyz multiplied by the derivative of the inside with respect to z, which would be xy. All right. So then, really the only thing you need to pull from this, and it just goes back to the relationships that we discovered, really, and that is the negative reciprocal aspect. All right. So if I'm looking for partial z with respect to y, if I have my partial with respect to y, negate that and put it over the partial with respect to z and call it a day. All right, so we've actually already solved the problem. It's just a matter of making the problem understand that it's already solved. All right, so negative 2xy plus cosine xyz times xz all over 3z squared plus cosine xyz times xy. So nothing too crazy.